Lesson 25, we will be able to explain how charge movement and electron movement are different. And we're going to talk about current and voltage. Now, voltage is a new idea. We've talked about current already. Let's grab a quick look at what our ideas of current are. Current is the flow of electric charge and has the symbol I. It's measured in amperes. And we said that it's 1 coulomb per second. We essentially are saying, when we talk about current, what we're saying is well, how much charge is moving every second? Is there a lot, or is there, like, not much? How many of these electrons are moving? Maybe it's not electrons that are moving, maybe it's charge. Maybe you've got a beaker with like lots of like salts and they're moving around. How quickly are they moving? That's what we're talking about when we talk about current. How quickly are these charges moving from one place to another? It's very close to this idea of speed. But I guess because we're not measuring how fast they're moving, we're really measuring how much of them are passing a particular point in a particular time. So we talked about milliamps, we talked about the movement of charge. Now, when we talk about the movement of charge, that's just Yvonne will deal with that. I'll deal with that in a second, sorry. So current is movement of charge. It doesn't have to be through wires. Remember, it can be through like, it can be through, a nerve ending. Electricity, charge can pass through a nerve. It can pass through the air. It doesn't have to be through wires. But when it is through wires, we can get a pretty good idea of how quickly something's moving. We talked about how if current can only work if there is a flow of electricity. So you've got a big like battery or a big tank that's full of electricity. It won't do anything unless there's something moving, unless the water is flowing. That's when we say, hey, there is a current because it's flowing. There is no current when the circuit's closed. When the circuit's on, there is a flow. We talked briefly about, well, if we're going to talk about flow, how do we define the flow? We said that conventional current is from positive to negative, and electron flow is from negative to positive. We use conventional current in the circuits we're going to be studying. I briefly, in like the last 2 minutes before we ran out of time, talked about ammeters. And then I said that we essentially, they have very low resistance, so they don't interrupt the circuit. And they can make a short circuit if you're not careful. And then and I talked briefly about digital multimeters. So today we're going to finish up talking about current. Again, remember, current is the movement of electricity. Then we're going to talk about voltage, which is all about linked to the energy. So when we talk about current, we're talking about how quickly it's moving. When we talk about voltage, we're talking about how much punch do these electrons have. It's one thing to have a lot of electrons that, aren't really, there are a lot of charge that doesn't really have much energy. It's different to talk about energy that's, maybe we don't have much of it, but it's got a lot of energy. I want to start with this idea here. And this is got to do with electron movement compared to charge movement. I like this idea here because it's a new sort of idea. Electrons don't move very far in a wire, okay? The current is simply, when we refer to current, we say the current is simply how quickly the charge is passed down a wire. When electrons move down a wire, it's actually not called, when we talk about electrons moving down a wire, we actually don't refer to it as current. We technically refer to it as electron drift. You might be saying, well, I don't get it. What do you mean? Let's grab a look. I want you to pick one of these electrons. Let's pick, wait for it, this one. So if we watch this one electron and it jumped, and we're going to wait, and it jumped. It's moving down the wire, right? But it's moving very slowly down the wire. It's actually, taking its sweet time to get down the wire. So, okay, it's moving very slowly. So what? Charge can move slowly. What I want you to do is I want you to watch now. So it takes about 6 jumps for the electron to get to the other end of the battery. What I want you to do now is I want you to watch this red light, this red positive charge. That moves from one end to the other end in one cycle. It's moving a lot faster. And the idea is that the electrons aren't moving very far, but the charge is. The charge, the positive charge, is moving through the wire quite quickly. The same is happening with the negative charge. All of these electrons are moving to the right. The negative charge is moving quite quickly, sorry, to the left. All the charge is moving quite quickly to the left, but the electrons aren't individually moving very far. Does that sort of make sense? Have I explained that well enough? Can I get like a yes in chat, or maybe just a yes out loud? Anyone? Got something in chat? Someone said, I'm hoping. Can you explain it again? Of course I can, Brendan. Sorry. Let me go through it again. I'm just going to go. So I'll go through a bit slower. What I want you to do is I want you to watch these electrons. Pick one. Let's, as I said, if you watch these electrons, we'll call this one cycle. We'll call this 2 cycle. It's going to take 5 jumps to get to the other end, right? So it's going to take the electrons 5 jumps, which is going to take 5 cycles. But if you watch the positive charge, which is the thing in red, the positive charges move from the left to the right in 1 cycle. It only takes 1 cycle for it to get to the other side. That's because the charge is able to move faster down the wire than the individual electrons. The electrons, sure, are carrying the charge. They are doing the moving, but they're only moving 1 step at a time. It's like, I guess, the difference between saying, imagine if you had an army, and the army were set up, and then everyone took a step forward, right, in this massive long army. If everyone took a step forward, each individual person doesn't move very far, but the whole thing is a big movement. Each electron doesn't move very far, but the whole charge moving down the wire is a big movement. So that's sort of the difference between electron movement and charge, and the difference between electron movement and everything else. So let's keep going now to talk about the next idea here. I want to talk to you a little bit more about electron drift. So let's actually do this. Electron drift velocity is dependent on the current, the thickness of the wire and the material it's made of. So how quickly these electrons move down the circuit is dependent on a couple of things. If you have a really thick wire, then you're gonna be able to let a lot of electrons through. If you have a very thin wire, the electrons aren't going to move as quickly. And so, yeah, you can actually calculate this as how long will it take? Let's look at an individual electron. How long will it take an individual, to take an individual electron to travel to a power point, from a power point to a laptop? Should be from a power point. From a power point to a laptop, if the drift velocity is 7.8 times 10 to the negative 5 meters per second, and there is 1.5 meters of copper wire to pass through, how long does it take the electron to get from the, from the PowerPoint to the laptop? How long does it take the one electron to get from here all the way up to here? You're like, okay, well, let's figure this out. The electrons are going to, we've got the drift velocity. Velocity equals the distance traveled over the time. Okay? So we want to know how long it's going to take. So we're going to use velocity times time equals the distance. And time equals the distance divided by the speed or the velocity, which is the distance is 1.5 divided by 7.8 times 10 to the negative 5, because that's how quickly it's moving. If I shove that in my calculator, drift velocity 1.5 divided by 2.8 times 10 to the negative 5 gives us 53,571. 53,571 seconds. If I actually take that and I divide that by 60.
So you use 2.8 instead of 7.8.
Ah, crap. Damn it. Okay, 1.5 divided by 7.8 times 10 to the negative 5 is gonna, oops, damn it. I did 7. I'll get there. I'll get there. One 9,230. Oh, 231 seconds. We could actually figure this out. If I divided this by 60, it's going to take 320 minutes. If I divide that by 60 again, I should, be able to figure out how many hours it's going to take. It's going to take about, which is equal to about 5 hours-ish. So that actually shows you an idea of how slow these electrons are moving. I guess the electrons aren't moving very quickly, but the charge is. I want you guys to think about that. It's like, okay, one electron comes out of the PowerPoint and goes into the laptop. It's going to take 5 hours to get there, but that doesn't mean that, oh, you have to wait 5 hours for an electron. Remember, there is a long line of electrons, and every single second a new electron is going into the computer. A new electron is getting pushed into that computer. That charge is still moving into that computer. That charge is a lot faster than an individual electron. The other reason why I always do these kinds of questions is because I want people to realize is that this is a solid wire. I get the feeling that sometimes people think that, oh, electricity is just like a pipe and you've got these electrons are sitting in that pipe and they're zooming down. That's not the case. It is a solid wire. These electrons are not zooming down the wire. They are bunched up and pushing against all the other electrons, and they're only moving a little bit. But that doesn't mean that there is not still a lot of electrons coming out. So it's a bit of a weird idea, but I like to get people to realize that because I don't want you guys to think about, and especially because as we talk about this a little bit more as models of electricity, I don't want you guys to think about them as being, I don't want you guys to think about them as being, oh, it's like a big long, it's like a tube. It's almost more like a conga line. If you think of a conga line, everyone's like, dancing, da, 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 da. Anyway, it's a big long conga line of people, waiting to get into the computer. and you can only walk as fast as the person in front of you. It might take you a while to get to the laptop in this conga line, but there's always someone walking through the door to the laptop every second. That's a bit of a weird analogy, but it kind of works. So that's electron drift. I briefly want to talk to you guys now about continuing this idea of current. There, not only do we have conventional current and non-conventional current, we also have two types of current. We refer to them as DC and AC, or AC and DC, or AC/DC. Yeah, that's where the that's where the rock band got their name from, pretty much. DC stands for direct current or directional current. What directional current is, it's when the current travels in the same direction. So if we watch in this example over here, we can see that that is always going the same way. Right? This is used in all kinds of devices around your home, from a TV to a refrigerator. This is the type of thing that batteries produce in circuits, but also like if you've got a TV, then it's going to have a DC. If you've got yeah, pretty much most electrical devices use DC current. It's called directional current because it has one direction. For the history buffs, this is actually what this is the kind of current that Edison thought was really important to look into. He was all about directional current. So directional current in one way. What's AC then? AC is alternating current. AC or alternating current is when the current changes direction and goes back and forth. So I want you to watch this one here. It's going to the right and then stop, and then it's going back to the left. And it's going back to the right, and it's going back to the left. And it's going to keep doing this. Now you might say to yourself, well, if the charges aren't moving, the current's not moving anywhere, so therefore there's not going to be any actual current here. But there is. Charges are still moving, so energy can still be provided. You still have to push these electrons, right? You're still pushing these electrons forwards, backwards, forwards, backwards. You are still applying energy to move these electrons. So therefore, you can still get power from, or electricity from this, and useful energy from this system. So why would we use AC? Why wouldn't we use DC all the time? AC is really good because AC current is used in transmission lines to provide large amounts of current. They are also the power that you use in your lights. So there is a reason why they're used in power lines. In general, they're used in power lines because they're just a bit more. It's just a bit more easy to move. It doesn't have as many problems with resistance, and yeah, it was just a lot more efficient. There's less energy loss when you deal with AC. So you might say, well, how quickly does AC work? AC actually changes its from forwards to backwards, right? 50 times per second. And it's going so quickly, so it's flickering 50 times per second, you don't actually see it. If you have your lights, like most home lights, are hooked up to AC, and if you turn your light on, you don't see it flicker. That's because it's changing in 50 hertz. And ultimately, humans can only realistically perceive 24 hertz. Like if you, for those fancy of you here who have 60 hertz monitors, that's flicking, that's changing screens every once 60 times in a second, but you can't actually see it. It just sort of smooths out. On the bottom here, we've got the two types of ways we've got DC voltages in red. We can see that that's a straight line because it's always got the same voltage, whereas AC has an alternating voltage, it goes up, down, up, down, up, down. And so that can be used. Now, I'm going to be honest with you guys, I haven't done a very good job of explaining why AC is better than DC in some circumstances. I know that but there is a reason for it being better. It's just a lot better at moving electricity from one place to another place. What we use them for is we use AC to move electricity, and then we turn it into DC to use in your house. So that's why they're the two types. And for those of you who want to know, AC was the brainchild of Tesla. And this is why the two, Tesla and Edison, got in a lot of arguments, because they were trying to just argue which one they thought was better. But ultimately, they're both good. They're just used in different, they're used in different times. Like, they're good for different situations. It's not a great idea to power, it's not a great idea to power something like a toaster using AC, because you wouldn't be able to move the electrons in the right way. It also is not a great idea to try to move a bunch of charge using DC, because the problem with DC is that you will lose electricity because of the other way. Let's keep going. So that's the two. Let's see, what have I got next? Oh, okay. So that's pretty much the end of my discussion on current. Okay. So just a quick reminder, current is the amount of charge moving in a second. Okay. 2, current, high current means a lot of charge moving in a short time. Low current means very little charge. We've got conventional versus electron flow. We've got DC versus AC. And then we've got a little bit about electron drift. But ultimately, when we talk about, and go back to the main idea, when we talk about current, we're talking about the movement of charge. Because now we're going to move on to a discussion of voltage. Okay, now before you guys ask, yes, I ripped this straight from Wikipedia. I did not write this myself.
Wikipedia.
Yep, Wikipedia, because I'm lazy. But the main reason that I wanted to do this, because I wanted to show you this. This is a voltage pile. Ultimately, where did electricity go from? Going back to a bit of a chat about our history, Luigi Galvani was a biologist and just general scientist. And what he was doing in 1780s, he was cutting up a frog. So he has this frog, and he's cutting up the frog. And what he does is he uses a brass hook. And when he uses the brass hook, he actually gets he accidentally touches his brass hook to his iron. I think he was using an iron scalpel, and actually he watched as one of the legs on the frog actually twitched, and he freaked out. I would freak out. I would freak out if I was trying to dissect a dead frog that had its head cut off, and then suddenly its legs started to twitch. You wonder where the idea of zombies sort of come from. Well, this is my opinion. So we've got this twitching thing, and he actually referred to this as animal electricity, because he kind of had this idea that, hey, it's a moving thing. It's very similar to the way that that amber moves things. So we call it animal electricity. It was kind of there was a bunch of other scientists that then said this is evidence of the soul and so on and so forth. But we're not going to get into that. What Alexander Volta did, though, his friend came over and he said, well, maybe we can replicate this without the frog. And so what he did was he got a bunch of copper discs, zinc discs, and brine, which has a lot of salt in it, and he made a repeating unit. And so copper, zinc, copper, zinc, copper, zinc, with all between them all was the salt solution, which actually meant that that charges could move. And what he did was we created something that we would later refer to as the battery. This voltage pile of battery was able to provide people with electricity, but unlike the Leyden jar, which made electricity when you charged it up, this created the charge imbalance by just existing. Now you didn't need to charge up a rod just to get, or use a motor or a Van de Graaff generator. You could get high amounts of charge disparity, like charge differences, all the positives on one side and all the negatives on another side. You could do that just by using a device like a battery. And that's where we start to talk about, okay, so there are devices that can do this for us. There are devices that can split positive and negative charge without actually, needing human intervention. What does that look like? Well, this gives us to the idea of voltage. What is voltage? Voltage is the amount of force needed to move the electrons. Well, you know what? I actually don't like that. But I'm gonna just, I don't like the amount of force. I'm gonna use the word energy. It's linked to the amount of energy needed to move the electrons, not really force, because force means you could measure it in newtons, and I don't want to get you guys confused. It's linked to the amount of energy the electrons have. It is measured in volts and has the symbol V. So when I talk about voltage, I'm talking about how much energy these electrons have. When I talk about voltage, if I take you might ask, well, one of the questions I usually ask students is say, well, if I took a PowerPoint, if I put my hand a meter away from the PowerPoint, am I at risk of getting electrocuted from the PowerPoint? Anyone tell me yes or no?
Yes, sir.
No. The answer is no. You're not likely to get electrocuted from a PowerPoint. The reason is because sure, that PowerPoint has a high voltage, but it doesn't have enough energy to move from the PowerPoint to your hand. You need a lot of energy to move through the air.
That was a joke, by the way, sir.
Yeah, I know, I got it, it's fine. I just, had to move on though. So if I took down here, right, if I took two rods, actually, it's more likely that this is the negative one, and this one's the positive one. If you were looking at this idea here, the electrons here have enough energy to move from one side to the other. They actually have enough energy to move through the air. If I lowered the energy or lowered the voltage, those electrons might not be able to jump. Hey, advanced question for you guys. Can anyone tell me why I know the one on the left, right is negative and the one on the left is positive? This is a bit of a hard question.
The one on the left.
What was that? Anyone know in chat?
Because the electrons are jumping from the negative to the positive.
Yeah, but how can I tell that they're jumping that way and not jumping this way?
Single
negative
point.
starts at one point.
Exactly.
Single point terminal.
Exactly. All the electrons are jumping from one point, right? But then some of them can go up, some of them go down. It doesn't matter. You might ask yourself, why is this glowing for? The reason this is glowing for is as these electrons are moving through the air, or as this charge, this electric field is moving through the air, it's ripping electrons away from their protons in, like, in a particular in a particular atom. But then as those electrons go back to the atom, they're going to release the energy that they absorbed to get ripped off. And when they release that energy, they're going to release it in the form of light. You guys might remember the flame test crack from year 9, where you put a piece of metal in the flame and it went green. That's the same idea. The electrons are gaining energy and they're losing it and they're emitting light. Same thing is happening here. They're gaining energy by getting ripped apart and then they're releasing it in the form of light. They would also release it in the form of heat, so that lightning bolt's going to get quite hot, but yeah. So voltage is got to do with the amount of energy. I like this example, and I made this example literally like a minute before I came online, but I wanted to show you guys this example here. I want you to compare voltage to gravity, okay? On the left, I've got a bunch of electrons and a bunch of protons, and on the right, I've got an apple. Now, if I raise the apple 8 meters, right, I've given it potential energy. I can drop that apple from that 8 meters or 8 centimeters high, and it will fall down and hit the ground. The higher I move the apple, the more potential energy that I give. If I put another apple up here, right? If I put another apple up here, I wouldn't have, you know, I would have 2 apples with the same energy, okay? I have more apples with the same energy. They can give overall, if I drop those apples, I'd have a higher amount of apples falling, but they have the same energy. Now over here, I want you to watch as I move these electrons up. These electrons also want to fall down, the same way how the apple wants to fall down. The apple wants to fall down because it is in a gravity field. I've done work on the system by moving the apple against the field. It wants to go down. I fought the field and moved the apple up, which gave it some potential energy. If I let this apple go, it will fall down and hit the ground, and it will do energy when it hits the ground. If I look on the left, I've moved these electrons up against the electric field. These electrons want to go down. They want to go back to the positives. I've moved them away. So what I've done is I've given these electrons potential energy. These electrons have energy because they want to go back to the positive. That's why the electrons move. They want to go back to the positive. The further up I move these electrons, the more energy they will have. Same idea happens with this apple. The further up I move it, the more potential energy it'll have, because the higher it'll fall down. The example would be if I drop this apple from 1 centimeter onto the ground, probably not going to make much of a difference. If I drop it from 10 meters up, it'll probably squash the apple because it will have a lot more energy. If I drop an electron from only a small distance away from the positive charge, it's not going to make a difference. If I move my negative charge really far away, then there's going to be a lot more energy that can be imparted. If in electricity, we refer to this as potential difference, because potential energy is created as I make a difference between the 2 points. As I raise these electrons up or move these or push these electrons together, then I'm going to create a potential difference. Potential difference is the same as voltage, and it refers to how much voltage can change. How much can this voltage change? So we would refer to this height as its voltage. If I move these electrons further up, then they would have a greater voltage because they would have more energy and will want to fall down more. And this is this is essentially what a battery does. A battery creates this imbalance. What a battery does, actually, I think I'll talk about that in another slide. Let's just cap off this slide here. I am moving the electrons against an electric field. I am pushing them apart. I'm adding energy, which creates potential energy or voltage. The further I move these electrons apart, the more potential energy I have. Now, this is a very complex idea. Okay, can I get people in chat? I want you to do me a favor. I want you, or you can say out loud. Maybe in chat's probably better because I'll have chat open. I want you to give me a between 0 and 5. 5 meaning you get this completely. 0 meaning you have no idea what's going on. 4 means you could get it. No, 4 means you get it, but you couldn't explain it to someone. 2 means you sort of get it. 3 means you get it, but you'll probably need some help. Yeah, okay, cool, beautiful. Yep. Yeah, all right, okay. Mostly 2s and 3s I've been seeing here on average. A lot of people sort of get the idea, but you know, don't get it completely. And I get that. It's a bit hard to talk about this stuff, but especially in isolation. But yeah, I want, even if you just get the idea that if the basic idea is, even if you just get the idea by moving positives away from negatives, I have to use energy to pull them apart. And then when I let go, it will release that energy. You almost think about the same sort of thing. A different field would be a magnet. Oh, if I have a magnet, and I move this up, I have to push and put energy to pull these magnets apart. But when I let these magnets go, they will release that energy as they come together. That's because you're pushing them against the magnetic field. As I release the apple, it will release the energy as it goes to ground. As I release the electrons, they'll release the energy as they go towards the positive charge. So, how can we, yeah, all right. How can we model this idea of, how can we model this idea of, how do I talk about this? How can we model this idea of a circuit? How can we model this idea of voltage and current at the same time? So imagine voltage is, imagine that the water in this tank up here, this is like our voltage. It's like our battery. The water in the top of this tank really wants to go down to the ground. It really wants to go from here down to this lower tank. For the same reason the apple wants to fall to the ground. If you have a cup of water and you turn that cup of water upside down, that water will spill out because it wants to go down in the gravitational field. It wants to get back down. Now we could just spill this water out of the tank and watch it go towards the bottom tank. Or we could force it to do something for us. So instead of letting the water just flow out into the bottom tank, we're going to get that water to go through a pipe. As it goes through the pipe, it might turn this turbine, it might turn this, you know, little pinwheel thing here and make this go round. This pinwheel is going to convert the energy from the water flowing into movement. So as the water flows, it moves this spinning dial, and then eventually that water is going to go down into this bottom tank. It's lost all its energy, okay? So it's gone from high energy to low energy. But that's not going to be very useful to us in the long run because eventually we're just going to run out of high energy water. So that's where this pump comes in. The pump moves the low energy water back up to the high energy, right? It's giving energy, it's adding work to the system. The pump is the same as a battery. Because now what we're going to do is we're going to compare this side here to this side here. So what a DC voltage source or a battery does is a battery in this situation is going to move the electrons from down here where there's like, you know, equal electrons to up here. What we're going to do is we're going to create an area where there is lots and lots and lots and lots and lots and lots and lots of electrons. And the battery has to do work to do that. The battery is trying to force all these electrons together. It's, you know, it's like a sausage party over here. It's like trying to get, you know, a bunch of men into a club. It's like, don't worry, guys. Like, you know, you're pushing all these guys into this club. It's like, well, there's too many guys here. I don't really want to hang out with a bunch of dudes. It feels a bit weird. It's like, well, just do it. That's what the battery's doing. These electrons, they don't want to be near each other because they repel. They really want to get away from each other. And they're going to say, well, get stuff, I'm out of here. And they get attracted to this end because this end of the circuit is positively charged. They have a lot of energy here. They have that energy because they are so compressed to each other. And they want to get to this positive side here. They're getting pushed away by the negative charge and attracted by the positive charge. That will force these electrons to go through the circuit, through something like a light bulb, that they'll lose some energy, and then they'll go through just so they can get to the positive side. They're attracted to the positive side. They want to get to this. When the electrons get here, they have low energy. They have lost their energy. They're exactly where they want to be. The electrons have now gotten to the positive charge. They're now neutral. And then you just got to wait for that battery to push the electrons back up to a higher energy state when they're all together. And the cycle will go on and on forever. So let's draw one more time the links between the idea on the left, the model to the left, and the model to the right. The pump gives energy to the electrons. The pump gives energy to the water. The battery gives energy to the electrons. It puts them in a higher energy state. The water doesn't want to be up in the air. It wants to be down the bottom. The electrons don't want to be all together. They want to be all split up with all these positive charges. These electrons will go through the circuit because they want to get away from this high energy area. The water will go through because it wants to get away from this high energy area. As it goes through this high energy area, it pushes, it does work on this motor, which is going to be movement. This one does work on the light bulb, which means it releases light. It then gets down to back to the positive end of the battery, which is a low energy state for the electrons and a low energy state for the water. This is an analogy that we're going to use a lot when we talk about circuits. That's why this is a model. A model is not an actual idea of how electricity works. It's an idea of how it works. It's sort of an explanation. The power supply transfers energy to the electrons, and so the electrons gain potential energy. The electrons converted into other forms. So this is why it's a good way to use this. One of the limitations though is obviously in a water cycle you can't see the electrons moving. You can't see the water molecules moving, so it's difficult to sort of compare the motion of the water because you just can't see through the pipes. So this is the idea here. I wanted to show you a different slide which sort of helps explain this a little bit more, is this graph here. At the top here, we've got a battery. And we've got the negative side of the battery, we've got the positive side of the battery, right? So F is the positive side of the battery, or A is the, hold on, other way around. Oh no, I think I was right. Hold on. Yeah. So if you look at the battery, if you start at A, right? At A, you know, that's where, like, on this graph here, it says this is the voltage or energy per coulomb. So at A, the current has a lot of energy because it wants to get back around to this side. As it moves through B, it will lose some of the energy, and it'll lose some of the energy because it's a globe. As it keeps going, it'll lose more energy at the motor until eventually, when it gets all the way back to F, which is where the current wants to get to, it will have no energy whatsoever, because that's where it wants to get to. It wants to get to this point where it's balanced. And then as it goes through the battery raises it back up to the high energy. It pushes all the electrons together. Now, this is a bit weird because I've done it in the direction of conventional current, not the direction of electrons. But remember, that's what we have to use when we talk about these things. So batteries use chemistry. Batteries use chemistry to create charge imbalance or a potential difference. Electrons will move around the circuit to correct this imbalance. When you create an imbalance, you are pushing electrons together when they don't want to go together. You are giving those electrons potential energy. They want to move away. And so that's how you get to this idea here. Are there any questions about this? Are there any queries or issues? I know this is a bit brand new stuff here, so if you've got any concerns, if you want me to go back over a particular point, I can. But otherwise, I'm going to keep moving forwards. Or I'm going to keep moving forwards because I haven't heard anything yet. I'm going to leave this up for a second. I'm just going to quickly check something. Sorry, because but at the moment, if you want to write this down in your books, you can. If you want to just take these notes, you can. If you want to try and figure this out, you're more than welcome to. I'll be right back. Sorry about that.
Damn. Sis got ass.
Sorry about that. I'm back. I hope you guys didn't miss me too much. Okay. Voltage is related to energy. I've just talked about how voltage is related to energy. But what does it actually mean to say something has a certain voltage? Voltage is related to energy in that it is considered to be the energy per a charge. So we've got a formula here. How much energy does a 9-volt battery give to 1.5 coulombs of charge? We can calculate that. Voltage equals energy per charge, which means that if I've got voltage times the amount of charge, I can work out the amount of energy. If I have 9 volts, and I multiply that by 1.5 coulombs of energy, then that's going to give me 9 times 1.5 is 13.5 joules of energy. So remember, of course, we measure energy in joules. So this is another idea here. Voltage is not just the energy, but it's the energy per coulomb. So if I have, you know, if I move, let me see if I can think of a way to talk about this. If I move, if I've got, I'm going to get this wrong. If I move these up 10. You know, if I give these electrons energy, right? I'm giving them potential energy as I'm moving them up. The voltage isn't just how much energy do I have, am I moving them up? It's how much energy do each of these have. So 10 would be linked to the voltage, which is why I've been using that as my example. I'm not talking about the total energy that's up here. I'm not talking about how much energy each of these electrons have or each of these charge carriers have. I'm talking about how much each of them have individually. They're each moving up 10. If I looked at these ones, they're each moving up 5. Now, if I knew how many electrons I was moving up, I could work out how much energy I have. If I move up, let's say if I move up 6 coulombs of energy up 5, if I move up 6 coulombs of energy up 5 volts, then that means that I've got, that's going to be 30 joules. If I move up 3 coulombs of energy up 10 volts, then that means I've got 30 joules. Remember, the voltage is how much energy each individual charge has. How much energy each individual charge has. We could even take this 13.5. We could even go one step further, right? I wanted to quickly show you guys this idea here, right? We've got 1.5 coulombs of charge, right? That means we can use that to work out how many electrons they have, right? So if I've got 1.5 coulombs, if I go 1.5 times if I divide that by 1.6 times 10 to the negative 19, that'll tell me how many electrons. So if I take 13.5 joules and I divide it by 1.6 times 10 to the negative 19, that will tell me how much energy each electron has. I'm going to do that really quick. 13.5 divided by 1.6 times 10 to the negative 19. Ladies and gents, I got this wrong. Sorry about that.
Oh no, the gumbo, Sonny.
I'm pretty sure what I've done here is I've tried to, divide the amount of charge. Realistically, if I've got 1.5 coulombs of charge, I should be multiplying that. I'm actually going to not do this because I'm going to make a mistake. And if I make a mistake, then I'm going to really kick myself later on. So I'm just going to leave it at the moment and I'm going to come back to it later on. But that's how we can figure out how much energy there is, how much energy all the charge has, how much charge you might have, and how much voltage. So it gives them a new idea of what voltage is. This is the same idea I just talked about before. The voltage is the pressure. This is here, we've got, again, another tank. Here is a bunch of energy that wants to flow down to the bottom. Is there, when the tap is off, is there pressure? Yes, there is pressure. It still wants to get out. In fact, this water wants to get out so bad, it's going to push against this tap here. When the faucet is on, there is still a push. The water is still pushing to get out. It still wants to get out. That's why it's flowing. That's why there is a current in the first place, because the water, the voltage, wants to get back to the ground. The same thing can be said here. Is there a push? Yes, there is a push before you open the switch. The electrons here really don't want to be all together. They would rather be up at this positive side. They can't get there, so there's no current. But the second you open the switch, then there is a current. Now these electrons can get to where they want to go. They will push their way through anything to get around to the other side. They will push their way through even a light bulb. And that's it. That's basically all of the explanation here. What we're going to do now is I'm going to admit that I'm not very smart and jump over to the textbook here and actually look at this example here so that we can see why Mr. Greer failed miserably. How much energy does, so it's a very similar question. They did the same thing and they figured out for their one, it was 0.75 joules. Then they said the energy is, and then they want to go, if a charge in the electron is 1.6 times 10 to the negative 19, how much energy does the electron have as it leaves the 1.5 battery? Well, let's look at how they did it. So they said the voltage is equal to 1.5, the charge is 1.6 times 10 to the negative 19. They just multiplied these two things together to find out how much energy each electron had. That's so much easier than what I was trying to do. So yeah, I kind of failed. Sorry guys. That would have been very easy to do. But yeah, each electron, when it leaves, has this much energy. When it gets back to the battery, it will lose that energy because it'll be where it wants to be. It'll be with a bunch of positive charge, which is where it wants to be. We talked about this stuff. We talked about this stuff. The only stuff we didn't talk about was, and because I hadn't made a slide yet, was voltage, voltmeters here. So a voltmeter is what you would use to measure voltage. How you measure a voltmeter is you put it in, and we're going to talk about these words later on. You put it in parallel, you force the electrons to go through the voltmeter, and what you do is you measure how much energy they release as they go through that voltmeter. And when you measure how much energy they release, you can get an idea of how much, what the voltage is. What I'm going to do, yeah, you know what? I'm going to set, and this is going to be the last thing, I'm going to set 3.4 as homework. You guys can spend, obviously you've got not much time left today, so maybe we'll spend some time on Thursday doing 3.4. I might even give you guys, might even not do a Zoom and just get you guys to do 3.4 instead. But yeah, that's going to be the homework. Are there any questions on what we've done today? I'm going to leave it here.